Okay, the recording starts now. Hello, welcome everybody to the Compiler's Reading Group. This week we're covering Chapter 4 and 5 of Joe Armstrong's thesis. Something like making reliable systems in the presence of sodware errors. We're going to go 136 again. And today we're covering two chapters. We're covering Chapter 5, which deals with errors, programming fault-tolerant systems, and we're dealing with Chapter 4, which is programming techniques. We skipped Chapter 3, which was covering Erlang. I thought that wouldn't be too interesting because it just covers the language, and the language itself it's fine. That's not really, that's not really the thing. That's not really when it matters. So I didn't find that too interesting. Chapter 4 is more interesting because Chapter 4 is actually writing some code, and I like code because I like programming techniques. And this chapter is quite good. I really like this chapter. I really, really like this chapter. It's quite nice. In this case, I want to go over the server implementation and the code. So this chapter kind of deviates from the rest of the thing where we have loadable code. And what's interesting is that we make servers, right? We make a server and some home locator, like I'm at this address type of work. And the server one's quite simple. You have an interface of start, stop, RPC, and loop. Right? Start starts the server, stop stops the server, RPC makes a remote procedure call. It's really quite simple, and loop just loops. And loop's private, right? There's some interesting things. Start takes a few things. It takes the name of the process, a function, and its initial state. Because our server is just a single function. This should remind everyone of Urbit, because Urbit is a single function operating system. This is a single function server. It's really not all that different. Stop stops the server. The RPC makes calls to it. So it gets interpreted by loop, which sends it to the function. So you make an RPC call. You're sending arguments to the function, and that's just how server 1 works. It's very simple. There is some complications of it. Namely, you have to understand Erlang's concurrency model, right? In this case, you have to understand that, you can spawn a process and then you can register its name through some registry system. And to stop the server, we send a message that's special to our loop that just quits, that just returns nothing. It just stops. And RPC, you have to send a message to the process and then receive things. It's all very Erlang specific code, right? Even loop is, you receive a message and you pattern match on the contents of what you get back. Server 1 is quite nice, but, it takes someone who's familiar with Erlang to write. However, let us write now the application code. And so this is called a very simple home locator register that Joe Armstrong wrote. It's very simple in that it has start. All it does is call the start function. So we're going to use server 1. And start just starts the server. Stop stops the server, right? And then we have a few client calls. Note that start starts the server with handle event. So handle event is like the looping function. Yes, Paul. Oh, am I not? Sorry, I thought I was sharing my screen. Oh, I was. Oh, yeah, section 4.3. Oh, sorry. Let me do that all again. Well, thank you. I should have realized I was sharing my not sharing my screen here. So here's what I wanted to show everybody. Here's server 1. I actually have the code. It's translated to Elixir from Erlang because that's just what I'm using for notation purposes. We have like the start function here. We have the stop function that I just described here. We have the RPC function and loop. So this was the server that I was kind of explaining, and you can see that start, stop, and RPC are the public interfaces, and loop is the private sort of function here that kind of doing all the work of just looping until it gets a message and then doing things. It's all, as I mentioned, highly Erlang/Elixir specific code. You have to understand the concurrency model. And so finally, for the actual practical code, you can see that when we make an application code, you have some way to start, which just starts the server. And all it does is call the start from the server that we're using, right? We're importing the start, stop, and RPC function. And we're starting with this function called handle event. This will be our main looping function. And the state will be new because we want a hash table of location, right? So this application is going to be like Joe is located at 6, and if and you can find Joe, you can ask where Joe is, and yeah, if you try to find Joe without registering him while he's not there, you can stop the server. All this is just using the normal mechanisms of the code itself of calling the server and hitting start, stop. For client functions like I am at, we just call the RPC with the message I am at, and we pass who and where. Same with find, right? Like, I want to find this person. There's only two functions, find and I am at. And it is quite nice because, well, I can just do it here. We can actually see here. So if I do one.start, I started the server, and I can try to find Joe. Joe's not there, and I can also say I am at Joe. Joe is at 6, and we can now see that we can find Joe. Right? This is the entire functionality, and so all find does is make an RPC call, and same with I am at. They just make the RPC call and call it a day, right? Which is quite nice. For the actual implementation, we're sending in the function handle event. And so handle event just does the pattern matching. It takes the I am at event and the find event and does the proper logic, right? I am at just adds it to the dictionary, and find just, fetches it from the dictionary, right? Just giving back error if it's not there. And this is the entirety of the code. Notice that we make no mention of Erlang's primitives. All we mentioned was this server right here. And all we expected from the server was start, stop, and RPC. Right? There is some issues with the server, but we'll get back to that in a second. Namely, well, if there is a bug in this code, that's actually an issue. It'll just freeze. Right? So to illustrate the point, I have a VHL R2. Let me just recompile my code. So I'll recompile VSHL R2. Great, I recompiled it. I want to stop whatever server that I had. Okay. Start. So now I started VSHL2, and I put a bug in here. If you put I am at, it will crash. It'll do 1 divided by 0 and crash, which is pretty horrible. So let's try it. I am at... Joe is at 6. And we can see that this code crashes and it hangs. It hangs forever. This server that we implemented does not really handle faults all that well. It expects that the function coming in is free of exceptions. It does not assume that it's a well-defined function. And because of this, when this function errors, it actually kills the REPL because it just, if you look at the logic, it just waits forever. RPC sends and then waits forever. There's no logic to stop, right? There's nothing like, oh, after a billion seconds, quit and stop trying to search for the packet. So the server is not particularly great, and there's no way of encapsulating errors, right? Because, well, exceptions. Like, if an exception were to occur, the server should handle it. The server should know what to do with kind of the exception. Like, it should report it back to the user and basically tell the user that your process died. And, there's definite mechanisms for restoring things, but we'll get that into a second. But because of this, let me actually turn this back to V8 server 2. So because of this, we implemented a second server. This server is mostly the same. The start is the same, stop's the same, but RPC is different, right? RPC sends a message, and either it expects that the code itself crashes, right? Like the the code it gets in can crash, and if the code can crash, no big deal. It just exit with the message RPC, right? Because the RPC message that you sent crashed the server, so just exit and give back the message. If you get back a reply, you get back a reply, and after a certain amount of time, it just exits. This is bad. It's mentioned in the paper that this is a bad way of handling it, and you should use supervisors instead. But this just shows you a very easy mechanism on like trying to solve these issues. And for the loop, all we really did was throw the code that calls the function in a try-catch, right? So we try it, and if it fails for whatever reason, log the error, right? It should log the error, the server crashed for a reason, and it should crash, right? So to demonstrate this, I have to recompile VHSLR2, and then we can do VHSLR2 start. So we start the server, and then we do the I am at Joe 6. And you can see here that it just exit with RPC. It doesn't free my node, like, you know, my code is still good. It just tells me that the server got crashed at I am at Joe 6, caused an exception of bad arithmetic. And from here, we can probably debug it further by knowing that, okay, so this is the input-output trace of it. What can you do? The error here is not as good as this, where this actually tells you a few things, like, oh, it died from this and from this helper, and that the target is invalid, right? So the way that we captured it's not the best, but it should show you that all we changed was saying use server 2 instead of server 1. That's the only difference, yet I get different non-functional behavior. If my code crashes, no big deal. It's quite good. And another function that this server, well, I'll get to that in a second. I want to get into our second version of very, very simple home locator registry. This code is exactly the same as the other version. Yeah, this code is exactly the same except it has an error, right? You know, and the issue is that this code is faulty, right? We introduced a bug into the code. Ideally, it should not have an error. However, we are in luck. Because we use server 2 has a thing called swap code. So server 2 has the ability to hot swap code. We did not have this ability in server 1. Server 1 had no ability of swapping out the function. But the great thing in server 2 is that it can just swap out the function, right? We just tell the server, hey, let's swap out the code with F. And server 2 will see this and be like, okay, cool, you want to swap the code? I acknowledge the change, and we're going to loop with the new function. The state is exactly the same. We offer no ability to change the state. Right? If you want to do that, you're going to need to modify the server. But what's great about this is we can undo our error. Right? Like here we have an error, so I'm just going to swap my code to the first server. Right? We have the first server's handle event, and it acknowledged it, and now when I say I'm at, it gives me back OK instead of crashing. So, you know, if I can find Joe, it gives me back 6, where if I find anybody else, like hello, it just, you know, just gives me back an error. So what's great is that this code, all it did to get the behavior of hot code reloading is just say server 2 instead of server 1. That's all you had to say. You didn't have to change the implementation. All the benefits were given in the generic reusable server code. So what we ended up having here is that this is purely functional code. There's nothing here that really does side effects, right? This handle event just puts things in a functional dictionary. It fetches things from a functional dictionary. If you really wanted to, you could throw static analysis tools at this, right? You could imagine that this is a pure subset, and you could actually prove properties about this code. It's not doing any multi-threading. It's not doing any of that. It's just sending back responses. Whereas the server code is very not functional, right? It's doing things like try catch. It's doing things like receiving messages from some type of message bus, right? It's sending and receiving messages, which is not a very functional thing to do, right? You're sending it to some process. You may not even get back a result, right? And you can even swap code, right? This is sort of functional, but it's sending a message to swap code. So, but you can see here that this encapsulates the functional behavior where you want it, and the minority of the code would really be in the server, right? The server is reusable. I don't have to make a new server for each application I'm making, the server, I can just use it. So what's great about this is that the required knowledge of Erlang expertise is minimal, right? The Erlang expertise is just tied to the server, but if we had real applications, the server is tiny. The application code would grow, right? Like if we wanted to make this more featureful, we would add new functions here, and this code would grow. The server really wouldn't grow unless if we're wanting better non-functional behavior, like, oh, I want my server to run in a better distributed way, right? And that takes a specialized skill set that not everyone has to know. So something great about this is that this kind of encapsulates functional and non-functional behaviors quite well. Like the mechanism that it uses is quite good. And this just shows it with a single function. In reality, it's kind of spoiling chapter 6, they do it on a module basis, where you send in a module instead of sending in a function, right? Because you have other constraints like async calls and non-async calls. Yes, Paul. Yes. It could mean both, but it depends. So for the most part, it does mean non-functional, as in like not required for the business logic. The business logic stays business logic-y. It doesn't get messed up by, oh, I need to worry about my concurrency here. So when whoever maintains it now has to, work around these concurrency primitives they may have zero knowledge about or care about. So it means functional in that sense, but it also means functional in a functional programming sense. Because if you look at this code here, it is functional in terms of functional programming. And it can stay functional. A lot of business logic's rather boring. Sometimes you do have to mutate things, like if you had a database connection, well, yeah, you may be mutating that database, right? The database may be a server somewhere and you may have to send messages, so things may still be imperative, but you can factor out imperative and functional code as well. So it kind of gives you mechanisms for both. Yeah, it's quite nice. I guess the only other difference in chapter 4 is that he mentions things like, I forget what the term was. It was intention programming. Oh yeah, I should get to errors. Another really interesting methodology is let it crash. I don't know if you noticed here, but it's okay if my handle event crashes. I actually don't care. It's not that big of a deal. But he makes a really interesting distinction. I think is quite important. He differentiates exceptions from errors. An exception is something the runtime system does. An error is something the programmer does not know how to handle. So not all exceptions are bad, right? Like if you're trying to open up, say, a file, but the file's not there, you may have a backup strategy for it. So that may not be an error. The file may just not be there, right? That may just be a usual circumstance. Because of that exception's not an error. However, if you're thought to have that file be there, it's like guaranteed by the spec that it is there, and it's suddenly not, well, then that becomes a real error to your system. And so he kind of classifies errors as things programmers don't know how to do versus exceptions of things the system doesn't know how to do. And he relates this to specs, right? He gives kind of this interesting example of like if you have an assembly operation and the spec only tells you what to do for load and store. He says the Erlang answer is to just do the load and store and have the system generate the error for you if a user tries to do some weird exception by saying, "Oops, I did it again," which is, I think, kind of the converse of how ML methodology handles things, because this is basically saying if it's not in the spec, don't even bother. Whereas, kind of in a more of an ML kind of specification, you try to be very exhaustive over a spec. I guess you can't handle literally everything, so this would still happen. If someone sends you a message that you actually cannot interpret, then I think you'd still have this. So I think this is a bit different from the ML methodology of exhaustion, but I don't think it's completely against it, because if some instructions are in the spec, then you'd have to handle it. Though I think this thing is saying that always being exhaustive doesn't matter But I don't know. It seems like it worked out for them. I don't really have an opinion on that. It's just an interesting contrast to kind of ML style error mechanisms. I've had arguments with people that know Java and work at big corporations who argue against exhaustion because they may receive all kinds of messages. So you see like this kind of pull and tug depending on what type of domain you work on. I would say this is probably a very domain specific trade-off, right? I would say this is probably a trade-off. And lastly, the last thing of the system is that they're like lookup. He noticed that lookup did a lot of things in the system. Like you can do like, oh, I look up and it's okay you're there, or you want to retrieve data from lookup, or maybe you want to search it. And so he ended up breaking up this function into like fetch is key and find, where one of these accepts. So he's basically arguing that your code should be readable and someone should just be able to look at your code and understand what it does. And there should be contract specifications of what these functions do, and it's important. And you can kind of see that in the docs of fetch, right? So if we go to map.fetch, fetch bang is one elixir. The spec, this thing can crash. This thing literally errors if it's not there. So you could fetch like this, but if you send in B, it'll literally error. Whereas something like what they use, what they call find, will just kin back an error, and you'll see this in specification. Because if we do this, we can see that its spec can give OK in value or error. So like this is like the difference in if you're using a more type-safe version of preludes in Haskell or OCaml. This fetch is like fetch error, is what the OCaml people call it. Whereas this is just fetch, which returns a maybe. And both of these are important because maybe per the specification, it ought to be there, right? It must be there, and you're erroring otherwise. So Erlang, makes it okay to like have an error like that. It's just kind of explicit in the sort of lookup you're using. So it's just kind of interesting that kind of lookup broke up into these three functions. So that's pretty much all of chapter 4. Does anyone have any like questions for chapter 4 or wants to note anything that I missed? I kind of just went over these servers here. And yeah.
Mentions that they first had the lookup function and then they split it up based on how people use the code.
Yeah.
So maybe you don't know exactly what the API should be until you've seen how the code is, how people use it.
Yes, that's a very...
And then be willing to change it.
Yeah, that's a very good lesson. I think a lot of systems suffer from that. If you looked at, for example, even for Urbit, because people were trying to still figure out the system, they didn't, say, use the namespace system well enough. And so they had a much more limited design in which rather it should have been used in a different way. But by the time they got ergonomic, they had issues. So yeah, sometimes you just have to use a system to kind of understand what patterns fall out. You see this all the time, even with a language like Factor. The language was rapidly evolving and changing things until it became stable because, well, it turns out that using things in a certain way is not ergonomic or it doesn't lead to the best ideas. So, I think that is a good lesson for planning for growth. I think it's a lesson for language design and system designs in general. You ought to plan for growth and you ought to look at how things are used in your system and seeing how things change. I would like to make one note. I accidentally in the recording had everyone muted until Paul started speaking lastly, so the recording may be a bit janky. I apologize. Anyways, yeah. Yeah, I do find it funny though that it was just tacked on at the end. Like he just added a section right here at the very end of just like, oh, intentional programming. Bye. It goes to discussion and then like, we're basically on chapter 5 at that point.
It's all been all about errors and stuff to that point. And then feels like it deserves its own section almost.
Yeah, probably. I agree. I don't know where it's slotted in. This is, what page is this? This is page 127. If I go to like page 1 and look at the thing here. The problem is that like it's kind of hard to fit it in because you have like programming techniques here, which it would be a programming technique, I guess. But like the rest of these are just like conclusion APIs. How did it work out in the real world? Case studies. So to me, it's kind of also a bit hard to kind of place it within how this thesis is laid out. So I'm guessing you really wanted to talk about it, so you just like threw it here. Yeah, cool. I guess now we move on to chapter 5. I don't have any code, sadly, for chapter 5, because chapter 5 didn't really have any running code. So we're going to just kind of go through the paper, which is, you know, a bit boring, but yeah. Essentially, he talks about programming fault-tolerant systems, and he talks about errors and how they work. Like, I think he talks about error mechanisms at the very start, and like, you know, how errors and exceptions are different, kind of like in chapter 4. But then he starts talking about supervisors, right? Supervisors are interesting in that it's mentioned here in a diagram. Where was the diagram? Man, I missed the diagram. He had a really good diagram. Wow, what a shame. I guess I missed the diagram. But basically, he mentions, I think, it may have been chapter 4, I guess. Whoops. That a node can't repair itself. So he talks about how like errors can occur on your system, but you don't know necessarily how to solve them. And because you don't know how to solve them, you don't need to, right? Because your code running in a process could be equivalent to a machine dying, another process may have to fix it, right? Like if some other computer is being faulty, maybe you spin that up on a different system that doesn't have hardware faults, right? So it's very interesting as well from a hardware error point of view, in that if someone is monitoring your progress, they may need to repair you, right? Joe Armstrong, in a talk that he gave, mentioned that, you know, if he was having a was it a heart attack or something, that, you know, he can't fix it himself. He can't give himself CPR. Oh, I think he said if he was choking, he can't give himself CPR. Someone has to give him CPR, right? Like he can't repair the error himself, so he has to rely on someone else fixing the error. And so Erling's error mechanisms kind of work like that. I guess that's part of chapter 4, and I just kind of skipped over the diagram. So to kind of show everyone in the video, you know, it's here. You can see that, like, if your computer crashes, another computer may need to see it. I guess I mixed up the chapters a bit. But yeah, this one I guess deals just more with supervisors and hypervisors. So basically, you have a node, right? So if you have a diagram like this, right? This is called a linear supervisor hierarchy, where you have a supervisor that monitors a worker process and another supervisor. The supervisor monitors a child and another supervisor, and this one monitors a child. And what's interesting about this is if a server lower dies, the server above it, the supervisor above it, can restart the code below it. And what's really nice is that if a message from the top says, I want to, you know, you should die, the servers will take care of their children, right? This server here, the supervisor, will send a message to its worker child that, hey, you should die now, and should send the server to its child supervisor and tell it should die, which this server then has the responsibility of telling its children to die. So you can make up these pretty elaborate dependency mechanisms. It's not really shown here in a linear supervisor hierarchy. It's kind of boring in that each thing has a thing and you just send a message down. So he kind of shows off this diagram where he talks about and or nodes as another strategy of supervision you can do, right? So we could have a supervised system that says, if one of my children die, like say worker 3 died, kill all the children and restart them, right? So if worker 3 dies, it will shut down worker 4 and worker 5 and restart the entire process, right? This may be useful on a thing like merge sort, where if one of the nodes dies, well, then you can't really complete your sort, right? Like I actually can't use the data from my other children. They need to restart the process because, well, some data is going to be missing, right? Like you know, there's not really a good way to sort at that point. I guess you can sort parts of it, but that's not really satisfying. But there's also other kinds of nodes, like an OR node, where if one child dies, restart it. This may be something in like a database connection where maybe you're trying to like fetch some data, and if it happens to fail, well, just tell the child to fetch again. It may just been a server timeout or something. You don't want to restart all the other work just because one fetch failed. And so this kind of sets up interesting hierarchies of tasks where parts of the nodes can fail, and that's okay. Not everything needs to be restarted, but you're kind of intentionally thinking about how your system behaves in terms of faults. So I think it's really interesting how these systems work. Here he also talks about errors again, which yeah, we talked about. Well, I guess we can talk about well-behaved functions. He also gets into the notion of a well-behaved function. A well-behaved function is a program that behaves close to its specification, and if the specification doesn't tell you to do something, error. And also make sure that there's enough information to isolate the error, right? You should always be thinking, what is additional information that you can send up that is helpful for diagnosing an error? So there's like, so some principles, and also I guess turn non-functional requirements into assertions that can be checked out runtime. So this is saying, well, you can check for these things, and if the assertion is broken, raise an exception. So it's basically just telling you to program to an interface. And I believe he also mentions that interfaces are not always given, so you do have to be careful and work. But he basically has a very strong opinion that you should not stray away from the interface. If the interface tells you to do something dumb, do the dumb thing. If the interface tells you to do the smart thing, do the smart thing. It's not your job to really change it. You should change the interface if you're wanting to change it, because that's what people are programming to. And what's good about this kind of technique is that this gives you strong interface boundaries. I think one issue in programming in dynamically typed languages that don't have strong boundaries is that if people start disobeying the spec, or if they don't have the spec, like hint JavaScript, then really it becomes a nightmare to work with. However, if you have strong specifications and like strong abstraction barriers in how the system works, those types of issues matter less. They can be caught for, and you have assertions for it. It's much like how I have like type checking in my common Lisp code, even though it is dynamically typed. It is a way of obeying the spec, because all this is really trying to enforce a specification on how we believe data should work. And types are a kind of specification on how data should be transformed, right? Sometimes you require more harder types, like dependent types, or in a dynamic case, you can do dynamic runtime checks of certain behaviors, like, these things are dependent in certain ways, right? All these are just trying to enforce the idea of a specification on how your code should work and how boundaries on your system ought to work. I think object-oriented systems like Smalltalk also are a pretty good example of this style of programming. And yeah, I guess that's most of chapter 5. I guess one other note is he says don't program defensively, because you follow the spec and if things crash, no big deal. So you have some interesting wisdom from Joe Armstrong, I think, in these few chapters. Does anyone have any questions of chapter 5? I covered it quite poorly. It was quite a good read, but yeah, I really do think like supervision trees are quite interesting in how things work.
Yeah, he references a paper about recursive restartability,
Mm-hmm.
and there are some good examples there of bad systems. So there's one about NFS,
Mm-hmm.
about how you can crash in the lock subsystem, can just break all clients.
Yeah.
And then there's this thing about July 1988, the USS Yorktown lost control of its propulsion system.
Oh.
A string of events got by data overflow. So it was not, you couldn't restart it, it needed to be towed back to port.
That's kind of funny.
So that was kind of funny. And then it mentions, and you'll like this, that there's a Unix thing as well, which is everything uses the temp directory.
Mm-hmm.
So if /temp becomes unavailable, then all your programs will hang on I/O system calls.
Yes, it does.
It can't be restarted without losing all the work in progress.
Yes, I've had that issue before. I've actually had that issue before. I've had my system basically lock up because I think it ran out of space on like disk to write files to temp, so it ended up like crushing my I/O horribly. I feel that pain immensely on Unix. Ugh.
Yeah, that's the paper there you're highlighting. Yeah.
Yeah, exactly. The recursive restartable thing. Can I click on this? I can't click on it, but it's similar to an report by Fox. Yeah, it'd be good. I want to probably include it in the video description, maybe. But yeah, no, I think those are pretty good examples of systems that I guess are not fault tolerant. I find locks an interesting case. Like locks are just kind of bad because if your program crashes halfway through, you're kind of foobarred. Like there's nothing really you can do at that point. I don't know how you really recover from a deadlock, other than you just, I guess you could tell the lock to drop itself if you killed the offending process, but that's kind of risky. I guess it's kind of, yeah, it's not very great. Yeah, does anyone have any other, I guess, comments on the chapter? Well, okay. That was, I think, a pretty good 2 chapters. I don't know when we'll restart again. I'm hoping for maybe chapter 6 and 7. Like, I actually already have the code for chapter 6. For a sneak peek, I have it here, and it deals with gen servers and like how code is actually written in Erlang, which is really neat. And I think it has its own lessons. Like I learned, I guess some for sneak peek for it. Like I kind of learned how like clients and servers kind of work. It's very easy, actually trying to reason about these distributed system topics in Erlang. I actually can understand what these things mean a lot easier because it's given me a pretty good model of computation. So I ended up implementing his examples in chapter 6. For those who are curious about my code, I also have test cases for the code in chapter 4. So I have tests that that server 2 can update and that server 2 crashes in my test case, because it ought to crash in this case. It's expected behavior in my case. So if anyone's interested, I can link the GitHub, and there are tests for this. So we can test that the server actually crashes properly. So if anyone wants to play along at home, they can just clone my repository and play with the server, or write it themselves. I had a lot of fun just writing code. That was like most of the joy, is looking at this Erlang code, learning about how Erlang works, and then looking at if Elixir changed at all. Because Elixir changes things. And in chapter 6, if when we cover that, you'll see how Elixir changes some things about Erlang. I have mixed opinions on that, but yeah.
Yeah, I was going to say, is it changing for the better in your opinion, or?
Sometimes, like they replaced a thing called Gen Event. I think it was Gen Event. They have their own thing for like system dependencies, and like this node relies on some previous computation that can parallelize, say, logging better. So they have some interesting patterns. I think it's the case of throwing more things on top of Erlang, really, because it's all derived from the OTP system. You can just implement it yourself in like, I don't know, like 10 lines. I think I may have the code somewhere in here. I think I have like registry. I like the registry system here. I have a few things that I learned along the way that just kind of are here that I made to deal with the differences between Erlang and Elixir. Some of the stuff is just out of date. For example, like in Erlang, you should not use Gen FSM. You should be using Gen StateM. You should be using Gen StateM. This is the new interface for it, right? Gen StateM. It provides a server that's really replaceable. It basically replaces Gen FSM. So I was also looking kind of if any of the stuff has been replaced, and it has been since Erlang OTP 20. Gen FSM stays in the system as is, but really, if you're writing new code, you should use Gen StateM instead. So some of the stuff is just Erlang updating as well since this thesis. But yeah, yeah, it's hard to say if Elixir changes things for the better or the worse. It depends. It's a case of throwing more things at language design and saying, well, now you have a more featureful language. Much like how in a previous chapter we dealt with agents. Like if you looked at my original code here, instead of dealing with GenServer directly, they have this agent thing which hides the fact that you're dealing with modules, and it gives you kind of like the function API that Joe mentioned. I believe in chapter 4 and 5, Joe also mentioned that there's no reason why it not ought to be a function as well. It's just how the system evolved that it doesn't work like that. I remember that like either actually that may have been in chapter 6. I may mix up my chapters, but this is a questionable addition. It's good and it's bad, right? Like it depends on how you really want to look at it and where you're coming from it from a language design point of view, and what you value. This is I'd say would be a subjective evaluation, of addition. So it depends. So I guess it depends who you ask on that. I don't have a strong opinion, other than I can see why people don't like the changes in Elixir. Like I can sympathize with them. So, yeah, great.